Welcome to the Deep Sleep Science Channel. For most of human history, the idea of building a home in space existed only in imagination. Scientists, writers, and engineers wondered what it might be like if people could live above Earth, floating in a permanent laboratory that circled the planet. Early space stations appeared in science fiction long before they became real engineering goals. Yet over time, as rockets improved and humans began reaching orbit, the idea slowly moved from dream to possibility. The concept of a space station began to take serious shape during the early decades of the space age in the 1960s and 1970s. Both the United States and the Soviet Union experimented with smaller stations such as Skylab and the Salyut and Mir stations. These earlier projects proved something very important. Humans could live and work in orbit for long periods if the right systems were in place. Those experiments taught engineers how to manage air, water, food, waste, and human health in microgravity. By the 1980s, scientists and space agencies began imagining a much larger orbital laboratory that could support international cooperation. Instead of one country building its own station, the vision slowly shifted toward a shared outpost where multiple nations could contribute modules, research, and astronauts. This idea eventually grew into what became the International Space Station. The station that exists today is the result of one of the most complex international engineering collaborations ever attempted. 5 major space agencies joined forces: NASA from the United States, Roscosmos from Russia, the European Space Agency, the Japan Aerospace Exploration Agency, and the Canadian Space Agency. Together, they represent 15 participating countries, making the ISS a truly global scientific project. Construction of the station began in 1998 with the launch of the first module, Zarya. Unlike most structures on Earth, the ISS could not be built all at once. Instead, it had to be assembled piece by piece in orbit. Over many years, astronauts and robotic systems connected new modules, solar arrays, trusses, and laboratories together while floating hundreds of kilometers above the planet. More than 40 major assembly missions were required to bring the station together. Space shuttles, Russian rockets, cargo vehicles, and crew spacecraft all played roles in delivering components to orbit. Each launch carried a carefully designed piece of the station that would later become part of the larger structure. The cost of building and operating the International Space Station is enormous, but it reflects the scale and ambition of the project. Over the decades, the total investment from all participating nations is estimated to be well over $100 billion. This makes the ISS one of the most expensive scientific projects ever undertaken by humanity. Yet the station is not simply an expensive engineering experiment. It has become a permanent research platform where thousands of scientific investigations have been carried out. Scientists from more than 100 countries have used the ISS to study biology, medicine, physics, earth science, and the behavior of materials in microgravity. Another fascinating aspect of the station is that it has been continuously inhabited since November of the year 2000. That means humans have lived in space without interruption for more than 2 decades. At any given moment, a small group of astronauts and cosmonauts are quietly orbiting Earth about 400 kilometers above the surface. Life on the station is very different from life on Earth. Astronauts float instead of walking, sleep in small compartments attached to walls, and watch the planet pass below them 16 times every day. From their windows, they see thunderstorms, deserts, mountain ranges, glowing city lights, and the thin blue curve of Earth's atmosphere. Despite its scientific purpose, the ISS also represents something deeply human. It shows that nations with very different histories and cultures can work together on a shared project in space. Engineers, astronauts, scientists, and mission controllers from around the world collaborate every day to keep the station operating smoothly. Perhaps the most remarkable part is that the station itself never truly stops moving. It travels around Earth at roughly 28,000 kilometers per hour, completing one orbit every 90 minutes. While people on the ground go about their daily routines, the station quietly circles the planet again and again. And somewhere up there, inside that vast structure of metal, wires, solar panels, and laboratories, a small group of humans continues their work. They conduct experiments, repair equipment, photograph Earth, and prepare for the future of exploration. Because in many ways, the International Space Station is not only a laboratory in orbit, it is also a stepping stone, a place where humanity learns how to live beyond our planet, one orbit at a time. The station moves through orbit at about 5 miles per second. That is such an immense speed that it can be hard to picture in everyday life, because almost nothing we experience on Earth travels with that kind of constant motion. Yet for the people on board, this incredible speed becomes part of the quiet routine of daily life, carrying them smoothly around the planet while they float through their work, meals, and rest. That speed is about 17,500 miles per hour. In ordinary terms, that is fast enough to cross entire countries in moments and cover huge distances before most of us would even finish a single thought. The astonishing part is that this speed is not a brief burst, but a steady orbital pace that the station maintains as it remains suspended around Earth. The International Space Station completes one orbit of Earth about every 90 minutes. So, while a person on the ground may still be moving through a normal morning or evening, the station has already traveled all the way around the planet. This means the crew lives inside a rhythm very different from the one we know, where the idea of a single day feels stretched across many complete loops around the world. In a single 24-hour period, the station circles Earth 16 times. That number gives a gentle sense of how active orbit really is, because the station is never still for long in relation to the world below. While cities wake, sleep, and wake again, the ISS keeps tracing its path overhead, returning over oceans, continents, deserts, and clouds again and again. Because of those 16 daily orbits, the crew sees roughly 16 sunrises and 16 sunsets every day. That means the changing light of day and night is not an occasional event in orbit, but something that repeats in a steady, almost dreamlike rhythm. For astronauts, the sky does not brighten and darken once across a long day, as it does for us. But many times, as Earth's curve and the station's motion keep bringing them into sunlight and shadow. The station's orbital path takes it over more than 90% of Earth's population. In a very real sense, the ISS spends its time passing above most of humanity, gliding over regions where countless lives are unfolding at once. That makes it feel less like a remote object belonging to one place and more like a shared outpost that silently crosses above much of the inhabited world. The ISS is large enough that people on Earth can sometimes see it with the naked eye near dawn or dusk. Even though it is hundreds of kilometers above the surface, it can still appear bright enough to be noticed without any telescope. There is something quietly astonishing in that idea, that a human-made structure in orbit can be visible to an ordinary observer simply standing outside and looking up at the right moment. NASA public viewing guidance notes that ISS passes are best seen within a few hours before sunrise or after sunset. At those times, the sky for observers on the ground is dark enough, while the station high above is still catching sunlight. That balance makes the ISS stand out clearly, creating one of the easiest and most beautiful ways for people on Earth to spot a working space laboratory with their own eyes. When the station is visible, it often looks like a very bright moving star. It does not usually appear with obvious detail from the ground, but instead as a clear point of light traveling steadily across the sky. That simple appearance can make the station feel both distant and intimate at once, because even without seeing its shape, you are still watching a real place where people may be floating, working, or gazing back down. Unlike an airplane, the ISS does not show flashing lights as it crosses the sky. That difference helps skywatchers tell it apart from normal aircraft, which usually blink and announce themselves with familiar patterns. The station is quieter in appearance, more like a smooth and continuous light, which adds to the calm impression it leaves during a pass. Unlike an airplane, the ISS also does not visibly change direction during a pass. It appears to move in a steady, even path, without the turns and corrections we expect from aircraft in the atmosphere. That calm motion is one reason it feels so striking to watch, because it seems to glide with great certainty, following the geometry of orbit rather than the shifting routes of air travel. The station is larger than a 6-bedroom house. That comparison makes the ISS easier to imagine as an actual living space rather than just a machine in orbit. Even though it is built from modules, laboratories, cables, and systems, it is also truly a place where human beings live for months at a time, carrying out daily routines inside a structure large enough to feel graph, like a real home. The station includes a 360-degree bay window area for observation. This is one of the most famous and beloved spaces on board, because it allows astronauts to look outward in multiple directions and take in Earth, space, and station operations. From there, the experience of orbit becomes especially vivid, with the planet curving below and the blackness of space stretching beyond. The ISS is 356 feet long from end to end. That is an immense size for something assembled in orbit piece by piece, especially when you remember that every section had to be launched, connected, and integrated in space. Its length helps explain why the station is not simply a capsule or lab, but a sprawling structure with many roles working together. That overall length makes the station about 1 yard shorter than a full American football field, including both end zones. This comparison gives a familiar sense of scale, because many people can picture the length of a football field far more easily than a measurement in feet alone. It reveals just how expansive the station has become, stretching through orbit with the presence of a large terrestrial structure. The station's solar array wingspan reaches 356 feet. Those enormous wings of solar panels are not decorative features, but essential power-gathering surfaces that let the station turn sunlight into electricity. Their reach gives the ISS part of its iconic shape, making it look less like a simple spacecraft and more like a vast engineered platform unfolding in space. NASA notes that this solar array wingspan is longer than the 262-foot length of an Airbus A380. That comparison connects orbital engineering to one of the largest passenger aircraft ever built, showing that the station's dimensions rival some of the biggest machines people usually encounter in modern transportation. It is a reminder that the ISS is not small in any ordinary sense, even though it floats far above us. Astronauts aboard the station have taken more than 3.5 million photographs of Earth. That means the ISS is not only a research laboratory, but also a remarkable observation point from which the planet has been documented again and again. Those images capture weather systems, coastlines, cities, deserts, rivers, mountain ranges, and changing light, offering a long visual record of Earth from orbit. The ISS travels a distance equivalent to a round trip to the Moon in about a day. This does not mean it goes to the Moon, of course, but it does mean that its constant orbital speed adds up to an extraordinary daily distance. Over the course of one ordinary day for the crew, the station covers a span so large that it matches one of the most famous journeys in human imagination. Up to 8 spacecraft can be connected to the station at the same time. That gives the ISS the feel of a true orbital hub, rather than a lone vehicle. Different spacecraft may arrive for crew transport, cargo delivery, research support, or rotation of personnel, And the station is built to accommodate that changing traffic while remaining a stable working Bruberal outpost in space. A spacecraft can arrive at the station as soon as about 4 hours after launch from Earth. That is a surprisingly short travel time when you consider that the destination is not just far above the planet, but also moving rapidly in orbit. It shows how precisely spaceflight can be planned, allowing a launch from Earth to meet a moving laboratory circling high overhead within part of a single day. The International Space Station is operated by an international partnership of 5 space agencies representing 15 countries. This makes it one of the clearest examples of long-term peaceful cooperation in modern science and engineering. The station is not the work of one nation alone, but a shared project in which many countries contribute hardware, research, planning, and people. Those 5 principal partner agencies are NASA, Roscosmos, ESA, JAXA, and CSA. Together, they represent the United States, Russia, Europe, Japan, and Canada in the station's core partnership. Each agency brings different capabilities and traditions, which means the ISS is not only an engineering system, but also a meeting point for many national approaches to spaceflight. A typical long-duration ISS crew consists of 7 people. That number is large enough to support science, maintenance, operations, and daily life, yet small enough that the station still feels intimate as a living space. In orbit, 7 people share work areas, meals, schedules, and responsibilities, while depending on each other in a very direct way. During crew handovers, more than 7 people can be aboard at the same time. That creates short periods when the station becomes busier and more crowded, as one crew overlaps with the next. These transition moments help pass on knowledge directly, allowing those leaving and those arriving to coordinate life and work before the station settles back into its more usual rhythm. The ISS orbits Earth with an inclination of 51.6 degrees. In simple terms, that angle determines how far north and south the station's path can reach as it travels around the planet. It is one of the key numbers that shapes where the ISS can appear in the sky and which regions of Earth lie beneath its repeated passes. That inclination means the station's ground track reaches as far north and south as 51.6 degrees latitude. So the ISS does not stay above one narrow belt of Earth, but spans a wide region of the globe. Its route carries it over a broad range of climates, nations, and oceans, giving the crew repeated views of many different parts of the world. Places farther north or south than 51.6 degrees latitude cannot have the ISS pass directly overhead. That does not mean people in those regions can never see it, but it does mean its orbital path has definite geographic limits. Even a structure that seems to roam the whole sky still follows precise rules set by orbital mechanics. Its living area includes 6 sleeping quarters. Those personal sleeping spaces matter because long-duration life in orbit still requires moments of privacy and rest. Even in a machine built for science and survival, there is room set aside for something very human, a small private place to sleep, to be alone briefly, and to keep some sense of routine. The ISS includes 2 bathrooms. That detail may sound ordinary, but in orbit, it reflects the careful planning needed for long-term habitation. Systems that seem simple on Earth become important engineering challenges in microgravity. So the presence of 2 bathrooms also points to the practical need for redundancy and dependable daily life. Support. The station also includes a gym for exercise. In space, exercise is not optional in the way it can feel on Earth, because the body changes in microgravity. The gym exists as a health tool, helping astronauts protect muscles and bones while living in an environment where normal gravity is absent. The pressurized module length along the major axis is 218 feet. This measurement helps describe the long central interior portion of the outpost where astronauts can live and work in a shirt-sleeve environment. It gives a sense of how much of the station is devoted not just to structure, but to enclosed human-usable space. The integrated truss length is 310 feet. The truss acts like a giant structural backbone, supporting major systems such as solar arrays, radiators, and external equipment. It is one of the reasons the ISS appears so broad and complex from the outside, with its long framework stretching across orbit. The solar array length across both aligned arrays is 239 feet. These arrays are central to the station's ability to function because they gather the sunlight that becomes electrical power for onboard systems. Their scale reflects the station's enormous energy needs, from computers and lights to life support and research hardware. The ISS has a mass of about 335 pounds. That huge mass shows how much material had to be launched, assembled, and maintained in orbit to create a permanent space outpost. It also reminds us that even in microgravity, the station remains a very substantial physical object with real inertia and structure. That mass is about 725 kilograms. Expressing it in metric terms offers another way to grasp the station's scale, especially for international audiences and engineering contexts. However it is measured, the number points to the same quiet truth. The ISS is an enormous built environment, not a tiny capsule drifting alone. Its habitable volume is 13,696 cubic feet, not counting visiting vehicles. That is the portion of space the crew can actually use as a living and working environment inside the station itself. In orbit, volume matters deeply, because the difference between cramped and workable conditions can shape everything from efficiency to comfort. Its total pressurized volume is 491 cubic feet. That larger figure includes all of the sealed interior space where pressure is maintained, even beyond the core habitable areas. It helps show that the station is a network of connected, controlled environments, rather than a single room or module. NASA compares the station's internal pressurized volume to that of a Boeing 747. That comparison gives a familiar mental image for the sheer amount of enclosed space involved. It suggests that the ISS is not merely a spacecraft in the common sense, but an orbiting built environment with an interior on the scale of a very large aircraft. 8 solar arrays provide about 75 to 90 kilowatts of power. That electrical output keeps the station alive and active, supporting experiments, communications, computers, pumps, and environmental systems. In a place where there are no local power grids and no simple repairs, reliable solar energy becomes one of the foundations of everyday life. The ISS electrical power system is connected by 8 miles of wire. That means the station is threaded through with a vast nervous system of electrical pathways linking its many components. Even in the silence of space, an intricate hidden network is always at work, carrying energy where it is needed. More than 50 computers control systems on the station. These machines help manage everything from operations and monitoring to safety and communications. In a place where timing and reliability matter constantly, computers become quiet partners in nearly every action the station performs. On-orbit software monitors about 350 or 000 sensors to support station and crew safety. Those sensors keep watch over temperatures, pressures, flows, positions, and many other details that humans cannot manually track all at once. The station is therefore not just inhabited, but continuously observed by its own internal awareness systems. Ground systems use more than 3 million lines of software code to support the station. This shows that the ISS is not only what floats in orbit, but also an enormous support network on Earth. The station depends on a hidden digital framework below as much as on the visible hardware above. The station itself uses more than 1.5 million lines of flight software code. That onboard code helps coordinate the many systems that must operate together in a harsh and isolated environment. It is part of the invisible architecture of the outpost, every bit as necessary as metal walls or solar panels. In the US segment alone, 44 computers run more than 1.5 million lines of flight code. This gives a more detailed glimpse into how much computation is embedded in even one part of the station. The ISS may look graceful from afar, but inside, it depends on a deeply layered technical brain. Those US computers communicate through 100 data networks. Rather than one simple communications path, the station uses many linked channels to move information where it needs to go. This makes the ISS feel less like a single machine and more like a carefully organized community of systems talking to one another. Those networks transfer about 400 000 signals, such as temperatures, pressures, and valve positions. So behind the calm appearance of orbit, a constant stream of information is always flowing. The station is endlessly measuring itself, reporting on itself, and quietly sustaining the conditions that let people live there. Through Expedition 60, the ISS had hosted nearly 3 JAO-00 research investigations from researchers in more than 108 countries. That makes it not only a home and engineering achievement, but also a global scientific platform. The work done there belongs to a remarkably wide community, with experiments shaped by people from all over the world. The large elements of the station were delivered on 42 assembly flights. Piece by piece, mission by mission, the outpost was built in orbit over time, rather than launched all at once. That gradual construction is part of what makes the ISS so impressive, because it was assembled in space through persistence, planning, and repeated cooperation. Of those 42 assembly flights, 37 used US space shuttles. The shuttle fleet played a central role in carrying major station hardware into orbit and helping astronauts perform the work of assembly. For many years, those missions formed the backbone of the station's physical growth. The other 5 assembly flights used Russian Proton or Soyuz rockets. This balance of launch systems reflects the truly international character of the station from its earliest construction period. Different vehicles, different agencies, and different engineering traditions all contributed to creating one shared outpost above Earth. Zarya was the very first module launched for the International Space Station, so in many ways it was the station's beginning point. Before the ISS became the large and complex structure people recognize today, it started with this single element placed into orbit. That makes Zarya an important starting chapter in the story of how a permanent human outpost in space was gradually built piece by piece. Zarya launched on November 20th, 1998. That specific date marks the true beginning of the station's physical presence in orbit. From that moment on, the long process of assembling a home, laboratory, and engineering platform above Earth had officially started, even though it would take many more launches and many more years for the outpost to reach its full size. Before any other modules arrived, Zarya orbited Earth alone for 16 days. During that brief period, it was not yet part of a sprawling station, but a single orbital building block, moving quietly through space by itself. It is interesting to imagine that before the station became a symbol of international cooperation and continuous human presence, it first existed as one lone module circling Earth in silence. At the beginning of assembly, Zarya provided orientation control, communications, and electrical power, while the rest of the station was still being built. That means it was not just an empty first piece, but an active and useful foundation. It helped keep early station operations stable and functional, giving later modules something reliable to join as the outpost slowly took shape. Unity was the second module of the International Space Station. With Unity's arrival, the station began to change from a single spacecraft element into a connected structure. This was an important step because the station was always meant to grow through linked modules, and Unity helped make that modular design possible. Unity was delivered to orbit aboard the Space Shuttle Endeavour in December 1998. That mission carried a crucial part of the station's early framework, showing how the Space Shuttle program played a major role in station assembly. Instead of being launched on its own rocket like Zarya, Unity arrived inside a shuttle mission specifically prepared to help connect the station's first major pieces. NASA identifies Unity as the first US piece of the station. That makes it especially important in the station's international history because it marked the beginning of the United States' physical contribution in orbit. From that point onward, the station would grow as a shared structure shaped by many countries, not as a project belonging to only one nation. The crew of Chesai 88 attached Unity and Zarya together in orbit on December 6, 1998. That connection created the first true joined structure of the International Space Station. It was a major engineering milestone because once those two modules were linked, the station was no longer just separate components launched into space, but the beginning of a real orbital complex. Unity was installed to Zarya using a combination of Endeavour's thrusters and its Canadarm robotic arm. This shows how carefully station assembly had to be carried out, with both spacecraft control and robotic precision working together. Even early in the station's construction, building in orbit required a blend of movement, timing, and mechanical coordination that could not be rushed. Astronaut Nancy Currie used the shuttle's Canadarm to grapple Zarya during STS-88. That was a very hands-on moment in the station's early assembly, even though the work was being done through a robotic arm rather than by touching the module directly. It highlights how astronauts often build space structures through remote tools, guiding machines with great care instead of using ordinary physical handling. Zarya was installed to Unity while Unity was still inside Endeavour's payload bay. That detail helps show how the first assembly work happened in a very controlled and carefully staged way. Rather than having both modules floating freely from the start, part of the connection process used the shuttle itself as a stable working environment during this delicate early construction phase. Unity provides living and working space for crew members. So although it is a structural connecting module, it is also part of the station's human interior. This reflects one of the central ideas of the ISS design. Modules are not only mechanical building blocks, but places where daily life, movement, work, and support activities all take place. Unity contains more than 50 000 mechanical items. That number gives a sense of how much complexity can be packed inside what might look, from the outside, like one simple cylinder. A station module is not just a shell, but a dense combination of brackets, connectors, supports, valves, panels, interfaces, and countless other parts working together. Unity contains 216 lines that carry fluids and gases. These lines are essential because a station module is full of systems that depend on controlled movement of air, water, and other substances. In space, life support and engineering systems rely on those hidden pathways, making the module more like a carefully built organism than a simple room. Unity contains 121 internal and external electrical cables. That means power and signals are carried throughout the module by a large wiring network woven into its structure. Just like the hidden plumbing and wiring of a building on Earth, these systems make the visible space usable, even though most people would never notice them at first glance. NASA says those Unity cables use 6 miles of wire. That is a striking amount when you think about it. because one station node is not very large compared with buildings on Earth, yet it still needs miles of electrical wiring. This reveals how space hardware often packs a tremendous amount of technical infrastructure into relatively compact spaces. Unity has a mass of 26,225 pounds. That large mass reminds us that every major station element was a substantial engineered object long before it became part of the finished outpost. Lifting something that heavy into orbit and then installing it correctly required major launch capability, careful mission planning, and precise on-orbit operations. Unity is 18 feet long. While that may sound modest compared with the full station, it is enough to create a meaningful internal passageway and connection point in space. In station design, even a module of this size can play a huge role because it links systems, routes people, and helps define how the whole complex is organized. Unity has a diameter of 14 feet. That width helps make the module usable as more than just a narrow tunnel. It gives astronauts enough room to float through, work around equipment, and connect other modules in a way that supports both movement and function. Zvezda became the third module attached to the outpost. Its arrival was especially important because it added major core functions that supported long-duration human occupation. With Zvezda in place, the station moved closer to becoming a true space habitat, rather than simply an expanding construction project. Zvezda automatically docked to Zarya on July 25, 2000. That docking was a key step in turning the growing station into a place ready for sustained habitation. Automated docking also shows the sophistication of spacecraft operations, where major pieces can join together in orbit through carefully engineered systems and precise navigation. NASA Station Assembly Reference says Zvezda provides living quarters. This means Zvezda is not only a service module full of systems, but also one of the places that supports the human side of orbital life. On a station, the idea of living quarters matters deeply because long missions require more than survival alone. They require workable, organized places for people to stay. The same reference says Zvezda also provides life support systems. Life support is one of the most fundamental needs for any inhabited spacecraft because people in orbit depend entirely on controlled systems for air, water, and safe environmental conditions. Zvezda therefore contributes directly to the ability of the station to keep human beings alive over long periods. Zvezda provides electrical power distribution systems. In a station with many modules and many functions, power has to be routed carefully and reliably where it is needed. This makes Zvezda part of the station's deeper infrastructure, helping ensure that energy is not merely generated somewhere else, but properly delivered across the outpost. Zvezda provides data processing systems. That means it also plays a role in handling information, not just physical support functions. In an orbital environment, data is as important as hardware, because computers and control systems must constantly monitor, interpret, and coordinate the behavior of the station. Zvezda provides flight control systems. These systems help the station manage its orientation and motion in orbit, which is essential for safe operations and proper alignment. Even though the ISS may look calm and steady from the outside, it depends on ongoing control to remain in the right attitude and to support docking, power collection, and thermal balance. Zvezda also provides propulsion systems for the station. This is important because the ISS is not simply left to drift with no ability to adjust. Propulsion support helps with maintaining orbit and performing required maneuvers, which means the station is not only a place to live and work, but also an actively managed spacecraft system. Zvezda provides ports for Soyuz crew vehicles. These docking locations are critical because they allow human transportation spacecraft to connect directly to the station. In practical terms, that means Zvezda helps make arrival, departure, emergency return capability, and crew exchange possible. Zvezda also provides ports for cargo vehicles. The station depends on regular deliveries of supplies, hardware, experiments, and other support items, so cargo access is essential to long-term operation. A functioning outpost in orbit must be supplied continuously, and docking ports are part of that lifeline. 5 European automated transfer vehicles docked to Zvezda's aft port between 2008 and 2015. That history shows how one station module can serve over many years as a recurring connection point for international spacecraft. It also reflects the truly multinational pattern of ISS operations, where different vehicle families from different partners come and go as part of the station's life. Harmony was delivered in October 2007. Its arrival marked another major stage in the station's expansion because Harmony became one of the central linking points for later modules and visiting spacecraft. By the time Harmony was added, the ISS was no longer just being assembled for habitation, but was also growing into a more capable scientific and transportation hub. Harmony acts as an internal connecting port and passageway to international science laboratories and cargo spacecraft. In simple terms, it functions like a central hallway and junction point inside the station. That may sound ordinary, but on the ISS, a well-designed connecting node is extremely important because it shapes how people, resources, and modules all relate to one another. Harmony is a utility hub that provides air for station systems. This means it is not merely a passageway, but an active support center distributing essential environmental resources. In orbit, air is not just something that exists naturally around you. It must be generated, moved, balanced, and managed through the station's internal systems. Harmony also distributes electrical power. So beyond being a connector, it serves as part of the station's deeper infrastructure network. Modules and laboratories need dependable energy to function, and Harmony helps route that energy where it is needed. Harmony also distributes water. Water on the ISS is a carefully managed resource used for drinking, hygiene, food preparation, and technical systems. A module that helps distribute water is therefore part of the station's life support backbone, quietly helping daily life continue. Harmony connects the Destiny, Columbus, and Kibo laboratory modules. That makes it one of the most important structural meeting points in the station's scientific layout. Through Harmony, major research areas from the United States, Europe, and Japan are physically brought together into one working orbital complex. Harmony distributes resources from the Trust to the Destiny laboratory. This shows how station systems are connected across different parts of the outpost, with one structure feeding another through carefully planned pathways. The station is therefore best understood not as separate rooms, but as one integrated network where support flows from one region into another. Harmony also distributes resources to ESA's Columbus laboratory. That means the European lab depends in part on Harmony not just for physical attachment, but for practical operational support. This kind of interdependence is one reason the ISS functions as a real system rather than a cluster of isolated modules. Harmony also distributes resources to Japan's Kibo laboratory. Again, this emphasizes the station's interconnected design. Kibo may be Japan's laboratory, but it is supported within a shared architecture that links international contributions together in a functional and physical way. Harmony's exterior serves as a work platform for Canadarm2. This means it is useful not only inside, where astronauts float through it, but also outside, where robotic operations can take place. On the ISS, many modules serve multiple roles at once, blending human habitation, structural connection, and robotic utility. Harmony provides international docking adapters on its space-facing port. These adapter locations are important because they make modern spacecraft docking possible in a standardized way. Rather than functioning only as a lab connector, Harmony also helps the station meet the changing transportation needs of later spaceflight eras. Harmony also provides an international docking adapter on its forward port. With more than one docking location, the station gains flexibility for visiting crew vehicles and changing mission traffic. This helps make the ISS more adaptable as spacecraft designs and operational needs continue to evolve. Those docking adapter locations support commercial crew vehicles. This reflects a major shift in the history of the station, where commercial spacecraft became part of regular human transport to orbit. The ISS therefore bridges different eras of spaceflight, from government-led assembly missions to a newer period that includes commercial orbital transportation. Columbus is Europe's largest contribution to the International Space Station. That makes it an especially significant symbol of Europe's role in human spaceflight. It is not simply a European attachment added for representation, but a major laboratory module that gives Europe a substantial and lasting presence in orbital research. Columbus is a multifunctional, pressurized laboratory. In other words, it is a sealed research space where astronauts can work in shirt sleeves while carrying out scientific tasks in microgravity. The word multifunctional matters because the lab is not limited to one narrow purpose, but supports a variety of experiments and technical activities. Columbus is permanently attached to the Harmony module. That permanent connection places it firmly within the station's central scientific architecture. Rather than being a temporary visitor or short-term element, Columbus became one of the enduring parts of the outpost's structure. Columbus lets researchers on the ground, with crew support, conduct experiments in weightlessness. This is one of the station's most powerful ideas. Scientists do not all need to be physically in orbit to use the space environment. The lab allows research teams on Earth to design and guide experiments, while astronauts help carry them out in microgravity. Columbus also supports experiments outside the module in the vacuum of space. That expands its usefulness beyond its internal laboratory environment. Some investigations need direct exposure to space conditions such as vacuum, radiation, and temperature extremes, and Columbus is designed to support that kind of work as well. Columbus has 4 exterior mounting platforms for external payloads. These platforms act like outdoor research sites attached to the laboratory. They allow instruments and experiments to be mounted outside the station, where they can observe Earth, study space, or test materials and technologies in the real orbital environment. Those exterior payload sites on Columbus can support space science investigations. That means instruments mounted outside the module can directly study the space environment instead of staying protected inside the station. In a very practical sense, Columbus is not just a room for indoor research, but also a platform that lets scientists place tools out in open orbit where they can examine conditions that simply do not exist on Earth. Those same exterior payload locations can also support Earth observation payloads. From orbit, instruments can watch cloud systems, coastlines, land changes, storms, and many other features of our planet from above. This makes Columbus useful not only for studying outer space, but also for helping scientists better understand Earth itself. They can also support technology experiments. That is important because the station is not only a place to do science about nature, but also a place to test new tools, materials, and systems that may be needed for future missions. Space is a demanding environment, so technologies that work there gain especially valuable proof of their reliability. Columbus has a mass of 22,700 pounds. That large mass shows that the module is a major structure, not a minor add-on. Launching something that heavy into orbit and then permanently attaching it to the station required serious engineering effort, careful transport planning, and exact on-orbit handling. Columbus is 22.6 feet long. That length gives the laboratory enough usable interior space for racks, equipment, and astronaut activity. In orbit, even a few extra feet matter because every section of pressurized volume must justify the cost and complexity of launching it into space. Columbus has a diameter of 14.7 feet. That width helps make the module feel like a real laboratory rather than a narrow tunnel. It creates room for equipment, storage, and crew movement, which is especially important when astronauts are working around sensitive experiments in microgravity. Columbus contains 10 payload racks. These racks act like organized workstations where scientific hardware can be installed and operated. Instead of being an empty room, the laboratory is carefully structured so many different kinds of experiments can be housed in a controlled and efficient way. Kibo is Japan's contribution to the station. That makes it a major part of the International Space Station's scientific identity, showing how the outpost was shaped by multiple nations bringing their own laboratories and expertise. Kibo is not just a symbolic addition, but an important working research complex within the larger orbital station. The name Kibo means hope. That gives the module a meaning that goes beyond engineering and function. In the setting of a long-term orbital laboratory built by international cooperation, a name like Hope feels especially fitting because it connects scientific work in space with a broader human sense of chaos. Possibility. Kibo was launched and assembled over 3 space shuttle missions. This tells us that the module was not delivered in one simple step, but required several carefully planned stages. Large space structures often have to be built gradually, and Kibo's assembly history reflects the patient, layered nature of station construction. Kibo allows astronauts to study a wide variety of space phenomena. That broad mission means it is not limited to one narrow field, but supports many different kinds of research in orbit. The module helps turn the station into a flexible scientific platform, where many questions about life, physics, and technology can be explored. Kibo experiments include biology. In microgravity, living systems can behave in unusual ways compared with life on Earth. So biological research in space can reveal things that are difficult to study on the ground. This makes Kibo a place where scientists can examine how living organisms respond when gravity is greatly reduced. Kibo experiments also include physics. Space offers conditions that allow physical processes to be studied without some of the constant effects we experience on Earth, especially those related to gravity-driven behavior. Because of that, the station can become a useful setting for examining physical principles in a different and revealing way. Kibo experiments also include technology research. This means the module is not only used to observe natural processes, but also to test tools, devices, and systems that may support future space exploration. Space is an ideal place to challenge technology because the environment is demanding, isolated, and unlike anything on the surface of Earth. Kibo includes numerous research racks. These racks let experiments be organized in a structured and repeatable way, with each rack serving as a dedicated location for specific equipment. In a laboratory where space is limited and every task must be planned carefully, this kind of internal order is essential. Kibo also includes an airlock for exposing experiments to the vacuum of space. That feature makes the module especially useful because it allows some experiments to move from the protected interior to the direct environment outside. In other words, Kibo supports both indoor orbital science and controlled access to the harsh conditions of open space. Tranquility provides extra room for crew members. On a long-duration station, extra room is more important than it may first sound, because habitability affects comfort, workflow, and mental well-being. Additional volume can make daily life feel less cramped and give astronauts more flexibility in how they move and live on board. Tranquility houses many of the station's life support and environmental control systems. This makes it one of the most important behind-the-scenes modules on the ISS, because it supports the basic conditions needed for human survival. Even if some labs get more attention, Modules like Tranquility quietly keep the whole outpost livable. Those systems in Tranquility include air revitalization. In simple terms, that means the station must constantly manage and refresh the air inside its sealed environment. Since there is no natural atmosphere flowing through the station from outside, systems like this are essential to keeping the cabin safe and breathable. They also include oxygen generation. That is a core requirement for any long-term orbital habitat, because oxygen cannot simply be taken for granted in space. The ability to generate it on board helps reduce dependence on supplies launched from Earth and makes the station more self-sustaining. They also include water recycling. Water is heavy to launch and extremely valuable in orbit, so being able to recover and reuse it is one of the station's most practical strengths. Recycling helps turn the ISS into a more efficient living system instead of a place that depends entirely on constant resupply. Tranquility contains a waste and hygiene compartment. That detail reflects a basic truth about space habitation. Everyday human needs do not disappear just because people are in orbit. A working space station must support not only science and engineering, but also hygiene, sanitation, and ordinary daily life. Tranquility also contains a treadmill. Exercise equipment on the station has a serious purpose, because astronauts need physical activity to help counter the effects of living in microgravity. A treadmill in orbit is therefore not about recreation alone, but about preserving health in an environment that changes the body. Tranquility is connected to the port side of Unity. This connection shows how the station grows through a branching structure, with one module joining another in a carefully planned layout. Every attachment changes the shape and internal flow of the ISS, linking living space, systems, and functions together. Tranquility can provide additional docking points for vehicles. That makes it useful not only as a support module for life on board, but also as part of the station's transportation architecture. Docking points matter because they expand the station's ability to receive spacecraft, hardware, and future operational flexibility. Tranquility was built for NASA by Thales Alenia Space in Turin, Italy, under contract to ESA. This fact reflects the deeply international nature of the station's construction, where modules may be designed for one agency, built in another country, and integrated into a shared orbital outpost. The ISS is full of this kind of cross-border engineering cooperation. The cupola is a small observation module on the ISS. Even though it is physically smaller than many other station elements, it has become one of the most recognizable and cherished spaces on board. That is because its importance comes not from size alone, but from the unique perspective it offers. It was designed for observing operations outside the station. This gives the cupola a practical purpose, beyond simply providing a beautiful view. Astronauts use it as a place to monitor external activity, making it both a working station and a lookout point within the orbiting complex. Those outside operations include robotic activities. That means the cupola is tied directly to the station's use of external robotic systems, such as Canadarm2. From there, astronauts can watch and help guide robotic work with a direct visual connection to the outside environment. They also include the approach of visiting vehicles. This makes the cupola an important observation point when spacecraft come near the station. In orbital operations, seeing how vehicles approach can add another layer of awareness during already careful and highly controlled procedures. They also include spacewalks. During extravehicular activity, the cupola gives crew members inside the station a valuable way to watch what is happening outside. It supports coordination and awareness during some of the most delicate and demanding tasks astronauts perform. Cupola has 6 side windows. Those windows help create the wide panoramic feel that makes the module so famous. Instead of offering just a narrow outward glance, the cupola was designed to surround the observer with multiple viewing angles. It also has one direct nadir window. A nadir window faces down toward Earth, which gives astronauts a remarkable straight-below view of the planet. This orientation makes the cupola especially powerful as a place for Earth observation and operational monitoring. Those windows give views of both Earth and celestial objects. So the cupola is not limited to one direction of interest. From the same small module, astronauts can look down at oceans, storms, deserts, and city lights, or outward toward the darkness of space and the wider universe. Cupola's windows have shutters. These shutters are practical protective features, not decorative additions. In the harsh environment of orbit, windows need shielding to preserve their condition and reduce exposure when observation is not taking place. Those shutters help protect the windows from contamination. In space operations, even small amounts of unwanted material can matter, especially on surfaces meant for clear viewing. Protecting the windows helps keep the cupola useful over long periods of station life. They also help protect against collisions with orbital debris. Space around Earth contains tiny, fast-moving objects, and even small particles can be dangerous at orbital speeds. The shutters therefore add a layer of protection to one of the station's most valued observation spaces. They also help protect against micrometeorites. These are small natural particles traveling through space, and at high velocity, they can still present real risk. The protective shutters help reduce the vulnerability of the cupola's windows to this constant orbital hazard. Cupola houses the robotic workstation used to control Canadarm2. This means the module is not only a place of quiet viewing, but also a center for hands-on external operations. Its design brings together sight and control, letting astronauts both observe and manage important robotic tasks from the same location. Quest is a pressurized airlock module. On a space station, an airlock is essential because it allows astronauts to move between the station's internal atmosphere and the vacuum of space in a controlled way. Without a module like Quest, spacewalks from the US segment would not be possible in the same manner. Quest consists of 2 compartments attached end to end. That 2-part arrangement reflects the need to organize the transition between inside and outside carefully. Different steps in preparation, suit handling, and depressurization are supported by separating functions into connected compartments. One of those compartments is the equipment lock. This part of Quest serves as a place where tools, suits, and support systems can be managed before astronauts head outside. In effect, it acts like a preparation area for one of the most demanding tasks humans perform in space. The equipment lock provides systems for suit maintenance. Spacesuits are complex life support machines, not simple clothing, so they need regular checks and care. A dedicated area for maintaining them helps ensure that every spacewalk begins with gear in proper working condition. The equipment lock also supports suit refurbishment. That means it is not just used for quick checks, but also for more involved upkeep and readiness work. Since suits must remain reliable over time, the ability to service them on board is an important part of long-term station operations. The other Quest compartment is the crew lock. This is the section astronauts actually pass through as they prepare to exit or re-enter during a spacewalk. In a practical sense, it is the final controlled threshold between the safety of the station interior and the open vacuum outside. The crew lock is the actual exit for spacewalks. So although Quest has support functions in more than one area, this compartment is the point where astronauts leave the station itself. It is the doorway through which some of the most memorable and technically demanding station work begins. Quest is the primary route for astronauts wearing US spacesuits to start and end EVA. That makes it one of the station's key operational modules, especially for maintenance, installation, and repair work conducted outside. Many important tasks on the ISS rely on this controlled pathway between pressurized interior and open space. Quest can also support the Russian Orlan spacesuit. This adds flexibility and shows that station systems are often designed with some level of interoperability in mind. In a multinational orbital outpost, support for more than one suit system can be practically valuable. POISC is also called Mini Research Module 2, or MRM-2. The name tells us that the module is both a research space and a smaller element within the larger Russian segment. Even modestly sized modules can serve several purposes at once on the station, combining science, support, and operational roles. POISC is almost identical to the earlier PERS docking compartment. That similarity suggests a practical design approach where proven configurations are reused rather than reinvented unnecessarily. In space engineering, repeating a successful design can improve reliability, reduce complexity, and build on experience already gained in orbit. POISC provides a docking port for Soyuz crew spacecraft. That means it serves as one of the places where the crew transport vehicle can connect directly to the station. A docking port is much more than a parking spot in space because it must support a safe physical connection, allow movement of people and supplies, and become part of the station's working structure while the spacecraft is attached. POISC also provides a docking port for Progress cargo spacecraft. This gives the module an important logistical role because cargo vehicles are essential for bringing food, equipment, spare parts, fuel, and other supplies to the station. In this way, POISC helps support the quiet but constant flow of material that keeps long-duration orbital life possible. POISC provides a place to prepare for Russian spacewalks. Before astronauts leave the station, they need a controlled area where procedures can be followed carefully and equipment can be readied step by step. That makes POISC more than a docking element, because it also participates in the practical preparation for work outside the station. POISC also supports refurbishment of Orlan suits. Spacesuits in orbit need ongoing care, inspection, and servicing, since they function as personal life support systems in the vacuum of space. By supporting this suit work, POISC becomes part of the maintenance cycle that keeps external operations safe and repeatable over time. POISC adds extra space for scientific experiments. Even a modest increase in usable station volume can matter, because research in orbit depends on having places to install hardware, store materials, and manage procedures. On the ISS, every additional area for science helps expand what can be studied in the unique environment of microgravity. POISC also includes power outlets for those experiments. That detail may sound small, but it is essential because scientific hardware usually depends on electricity for operation, control, sensing, or recording. A research space without access to power would be limited, so these outlets help turn POISC into a more functional working area. Razvit means dawn in Russian. The name gives the module a gentle symbolic character, adding a human note to a highly technical piece of station hardware. On a station made of metal, wiring, software, and docking systems, names like this remind us that people still bring meaning and language into the design of spaceflight. Razvit was delivered by Space Shuttle Atlantis on the STS-132 mission. That shows how station assembly often involved cooperation between Russian-built modules and American shuttle transport. It is another example of how the ISS was not created through isolated national efforts, but through missions that linked contributions from different programs together in orbit. Razvit is used mainly for cargo storage. Storage may sound less dramatic than laboratories or observation windows, but it is one of the basic needs of any long-term orbital outpost. Space stations must hold tools, supplies, spare equipment, and many other items in an organized way, and a module dedicated largely to storage helps support that everyday practicality. It also supports some payload operations. That means Razvet is not limited to being a simple storeroom, but can also help with selected scientific or technical activities. On the ISS, modules often serve more than one purpose, and that flexibility helps make the overall station more useful and efficient. Razvet is attached to the Earth-facing port of Zarya. Its position within the station's structure helps define how the Russian segment is arranged and expanded. Module placement matters because each connection affects docking options, internal pathways, and the overall geometry of the station. Razvet was developed by RSC Energia. This reflects the role of major aerospace organizations in building the different elements that make up the station. The ISS is not only an international project at the agency level, but also the result of work by many engineering teams and industrial groups contributing specialized hardware. Razvet provides a fourth docking port on the Russian segment. Additional docking ports expand the station's flexibility by allowing more visiting vehicles and more varied traffic patterns. In orbital operations, the number and placement of ports can shape how crews, cargo, and spacecraft are managed over time. Soyuz spacecraft can use Razvet's docking port. This means the module supports human transportation functions directly, helping connect crew-carrying vehicles to the station. The ability of Soyuz to dock their adds, another layer of operational resilience, and options for crew arrival and departure. Progress spacecraft can also use Razvet's docking port. Since Progress vehicles are central to resupply and support on the Russian side of station operations, this compatibility is very practical. It means the same module can contribute to both human transport and cargo logistics, depending on mission needs. Razvet has a mass of 11,188 pounds. Even though it is smaller than some major station laboratories, it is still a substantial orbital structure. Any module of this mass must be carefully launched, handled, and integrated, which again shows how much effort goes into every added piece of the station. Razvet is 19.7 feet long. That gives it a meaningful amount of interior and structural extent within the station complex. In the environment of orbit, dimensions like this are important because they shape how much space can be used for cargo, operations, or future flexibility. Razvet has a diameter of 7.7 feet. This narrow width, compared with some other modules, reflects the different roles modules can play depending on design and purpose. Not every station element must be wide and spacious. Some are optimized more for function, connection, or storage than for broad working volume. The permanent multi-purpose module was derived from the Leonardo logistics module. That means it began as a cargo carrying element, rather than as a permanently attached room from the start. The conversion of Leonardo into the PMM shows how station hardware can evolve over time, with earlier mission tools later taking on new long-term roles. The PMM is Italian-built. This is another reminder that the station's structure reflects contributions from many countries, each bringing different elements into the final shared outpost. The ISS truly is a patchwork of international engineering, assembled into one functioning home in orbit. Before becoming permanent, Leonardo ferried cargo back and forth to the station. In that earlier role, it acted more like a transport container than a fixed part of the complex. Its history is interesting because it shows how a useful logistics module was later given a second life as a permanent station element. The PMM added two 472 cubic feet of pressurized volume. In orbit, additional volume is always valuable because it creates more room for storage, work, and movement. This extra space helps reduce crowding and gives the station more flexibility in how it organizes equipment and daily operations. That added volume is used for storage. Storage capacity is one of the less glamorous but most essential parts of station design, since many items needed for long missions must be kept on board in an orderly way. Every extra place to store supplies can make life and work on the station easier to manage. It is also used for scientific work. So the added space is not only a place to keep things, but also a useful extension of the station's working environment. When pressurized volume is available for science, even a former logistics module can become part of the station's broader research mission. The PMM can hold up to 16 racks of equipment, experiments, and supplies. That means it is organized to handle a large amount of station material in a structured way. Racks are a fundamental part of how the interior of the ISS is arranged, helping modules function like carefully planned technical rooms, rather than loose open spaces. The PMM also has an end cone with extra storage space for cargo bags and other items. This reflects the station's habit of making use of every possible internal area. In orbit, even oddly shaped spaces can be valuable when there is always a need to place equipment, supplies, and materials somewhere secure. The ISS Environmental Control and Life Support System is called ECALS. This name refers to the collection of systems that make the inside of the station habitable for human beings. Without ECALS, the ISS would just be a structure in orbit, because people could not safely breathe, drink, manage waste, or remain in a stable environment on board. ECALS controls atmospheric pressure on the station. Pressure is one of the most basic conditions needed for human survival, and in a sealed spacecraft, it cannot be left to chance. The station therefore has to actively maintain the right pressure level so the crew can live and work safely inside. ECALS includes fire detection and suppression functions. Fire is one of the most dangerous risks in a closed space habitat because there is nowhere easy to escape, and even a small event can quickly become serious. That is why fire monitoring and response are built directly into the station's environmental support systems. ECALS helps control oxygen levels. The crew depends on oxygen every moment, so this is one of the station's most important ongoing tasks. In a space habitat, oxygen must be measured and managed continuously, because the atmosphere inside is entirely artificial and must be kept within safe limits. ECALS provides proper ventilation. Air in the station cannot simply move naturally in the same way it does in ordinary buildings on Earth, especially in microgravity. Ventilation systems help circulate air, prevent stagnant pockets, and make sure breathable conditions remain evenly maintained throughout the station. ECALS also handles waste management functions. This is one of the unglamorous but absolutely necessary sides of living in space. Long-term habitation requires systems for collecting, processing, and managing waste safely, because nothing can simply be discarded carelessly in a sealed orbital environment. ECALS provides water supply functions. On the ISS, water must be carefully delivered, stored, cleaned, and reused, since it is far too valuable to waste. A dependable water supply system is therefore one of the foundations of daily life, supporting drinking, food preparation, hygiene, and technical needs. ECALS has 3 key components. This helps us understand that life support is not one single machine, but a collection of coordinated subsystems. Each one focuses on a different part of keeping people alive and comfortable, and together they form the environmental backbone of the station. One key ECALS component is the water recovery system. This part is responsible for reclaiming and purifying water so the station can reuse it, rather than depending entirely on new deliveries from Earth. In an orbital habitat, recovering water is one of the smartest and most necessary ways to improve long-term sustainability. Another key ECALS component is the air revitalization system. As its name suggests, this system helps clean and refresh the air circulating inside the station. Since the ISS is sealed off from Earth's natural atmosphere, air must be actively maintained rather than simply taken for granted. A third key component is the oxygen generation system. This is the part of life support that helps produce breathable oxygen on board. Its presence reduces the station's reliance on supplied oxygen and makes the ISS more capable of supporting long stays in orbit. The water recovery system reclaims wastewater from crew urine. This may seem surprising at first, but it is one of the most practical and necessary features of long-duration spaceflight. Water is too important and too expensive to launch in large, wasteful amounts, so recycling it becomes a central part of survival and efficiency. It also reclaims humidity condensate from cabin air. In other words, moisture released into the air by human breathing and activity does not simply disappear. The system captures this water and brings it back into the station's recovery loop, helping make use of resources that would otherwise be lost. It also recovers water from the hydration system in EVA suits. Even the water used in support of spacewalks becomes part of the larger recycling picture on board the ISS. This shows how deeply the station is designed to capture and reuse resources from many areas of daily and operational life. Recovered water must meet strict purity standards before use. Recycling in space does not mean lowering standards. In fact, the water has to be carefully purified and checked before the crew can safely rely on it. This ensures that reuse is not just efficient, but also dependable and safe. Water from the urine processor is combined with other wastewaters before treatment. This means the station's water handling is part of a broader integrated system rather than a series of completely isolated streams. Combining sources allows the recovery system to process and refine them as part of a planned purification cycle. The water processor uses multi-filtration beds to purify water. These filtration stages help remove unwanted substances step by step, improving the quality of the recovered water. In a place where clean water is essential and resupply is limited, layered purification methods are an important safeguard. It also uses a catalytic oxidizer. This adds another level of cleaning beyond basic filtration, helping break down remaining contaminants. Together, the filtration and oxidation steps show how seriously the station treats water recovery and how much engineering goes into making recycled water usable again. Water purity is checked by electrical conductivity sensors. These sensors help determine whether the treated water meets required standards. Instead of relying on guesswork, the station uses measurement and monitoring so that the crew can trust the quality of the water they use. Water that does not meet standards is reprocessed. That means the system is designed with quality control in mind, rather than assuming every cycle will succeed perfectly the first time. Reprocessing adds reliability, helping ensure that only properly treated water is ultimately accepted for crew use. Clean water is stored in a tank for crew use. Once the recovery and treatment process is complete, the purified water becomes part of the station's usable supply. That final storage step turns the recycling system into something practical for everyday life, making recovered water available just like any other onboard resource. NASA says the water recovery system currently recovers about 90% of the water on the station. That is a remarkably high level of reuse and one of the strongest examples of closed-loop living in human spaceflight. It shows that the ISS is not merely consuming supplies from Earth, but increasingly functioning as a system that recovers and reuses what it already has. NASA also says this system reduces dependence on delivered water by 65%. In simple terms, the better the station gets at recovering water, the less new water has to be launched from Earth. That saves cargo capacity, reduces mission burden, and makes long-duration orbital life more practical. That improvement cut daily delivered water demand from about 1 gallon to about 1/3 of a gallon per crew member. This gives the recovery system a very human scale, because it shows how much resupply need has been reduced for each individual on board. Over time, a change like that has a major effect on how efficiently the station can be supported. The air revitalization system cleans the circulating cabin air. Inside the station, air is always being breathed, moved, and reused, so it must be actively maintained. This system helps keep the atmosphere inside the ISS healthy and workable for people living in a sealed environment far above Earth. It removes trace contaminants produced by electronics. On a space station, even ordinary equipment can release tiny, unwanted chemical byproducts into the air over time. Because the crew lives in a closed environment, these contaminants cannot simply drift away into a larger atmosphere, so the air system has to find and remove them to keep the station's environment safe. It also removes contaminants from plastics. Many materials used inside spacecraft can slowly release small amounts of gases or particles, especially over long periods. In a sealed orbital habitat, even subtle material off-gassing matters, so the air system helps clean up these invisible byproducts before they can build up. It also removes contaminants from human off-gassing. Human beings themselves release moisture, carbon dioxide, and other trace substances into the air just by breathing and living. On Earth, this happens in the middle of a vast atmosphere, but on the station, the air is limited and shared, so life support systems must constantly manage the chemistry of the cabin. The system removes carbon dioxide exhaled by the crew. This is one of its most important jobs, because carbon dioxide naturally builds up when people breathe in a closed environment. If it were not removed effectively, the air would become unhealthy. So the system quietly performs a task the station depends on every hour of every day. Trace contaminants are removed through 3 separate treatment units. That layered design helps make the cleaning process more reliable and more thorough. Instead of depending on a single method, the station uses several stages, so different kinds of unwanted substances can be handled in different ways. One of those units is an activated charcoal bed. Activated charcoal is useful because it can trap certain contaminants as air passes through it. In simple terms, it acts like a filtering stage that helps catch unwanted substances before the air continues through the rest of the system. Another is a catalytic oxidizer. This unit helps break down contaminants through chemical reactions rather than only trapping them physically. That makes it a powerful part of the system, because some substances are better handled by being transformed into safer forms rather than merely collected. Another is a lithium hydroxide bed. This gives the system yet another way to remove specific unwanted substances from the cabin atmosphere. In life support, redundancy and multiple treatment methods are important because the air must remain safe under many different conditions over long periods. Carbon dioxide is removed using molecular sieves. These sieves work by selectively capturing certain molecules from the airstream, allowing the atmosphere to be cleaned in a very controlled way. It is a quiet but impressive example of how chemistry and engineering are combined to make human life in orbit possible. The oxygen generation system produces breathable oxygen for the crew. That means the station can actively create one of the most essential elements for human survival instead of depending only on stored supplies. This capability is one of the reasons the ISS can support long missions and function more like a true orbital habitat. The oxygen system includes an oxygen generation assembly. This is the part that directly carries out the process of making oxygen on board. In a practical sense, it is one of the station's most important life support tools, turning water and electricity into a breathable atmosphere. It also includes a carbon dioxide reduction assembly. This means the oxygen system is not working alone in isolation, but is linked to other atmospheric processes taking place on the station. The combination helps support a more efficient and more circular life support loop. The oxygen generation assembly electrolyzes water. In other words, it uses electrical energy to split water into its component gases. This is a clever and powerful approach because water becomes not just something to drink, but also a raw material for producing life support resources. Electrolysis splits water into oxygen and hydrogen. That scientific process is simple to describe, but extremely useful in orbit. By separating one substance into two useful gases, the station can support breathing needs and also make use of the hydrogen in other system functions. The oxygen is released into the cabin atmosphere. Once produced, it becomes part of the breathable air the crew depends on every day. This step turns an engineering process into something directly tied to human survival and comfort inside the station. The hydrogen can be vented to space. That means not every byproduct must stay on board if it is not needed. Venting gives the station one way to manage excess hydrogen safely as part of the life support process. The hydrogen can also be fed into the carbon dioxide reduction assembly. This makes the system more efficient because the hydrogen does not always have to be discarded. Instead, it can be used in another stage of the station's atmospheric management, helping connect one support process to another. Astronauts work out at least 2 hours a day to reduce muscle and bone loss in microgravity. In space, the body does not experience the same constant pull it feels on Earth, so muscles and bones can weaken over time without regular exercise. The station's daily routine, therefore, includes exercise as a serious physical countermeasure, not just a fitness habit. NASA explicitly links that daily exercise to the need to reduce muscle and bone mass loss. This makes clear that the exercise requirement is based on biology and medicine, not on personal preference. The station is a place where even staying healthy requires carefully planned effort because the environment changes how the body behaves. The station's gym is therefore not a luxury feature, but a health countermeasure. It may sound unusual to describe a gym as part of a survival system, but in orbit that is essentially true. Exercise equipment helps protect the crew from the physical effects of long-term weightlessness, making it part of the station's medical strategy. The presence of a waste and hygiene compartment in Tranquility shows that core daily life systems are integrated into the station's modules rather than isolated in one tiny area. This reflects how the ISS was designed as a real living environment instead of a purely technical machine. Everyday human needs are built directly into its architecture, side by side with science and engineering systems. The 6 sleeping quarters listed in NASA facts mean the ISS was designed for private rest spaces, even within a shared orbital habitat. Privacy is limited on a station, so having dedicated sleeping areas helps support mental comfort as well as physical rest. These small personal spaces show that habitability matters in long-duration spaceflight. The station's 2 bathrooms reflect the need for redundancy in long-duration living. If one system has a problem, the crew still needs another available option because daily life cannot simply pause. Redundancy is a common principle across station design, and even something as ordinary as sanitation follows that rule. The station's water system recycles crew moisture as well as urine, so even breathing and perspiration indirectly contribute to the life support loop. This is one of the most striking examples of how tightly resources are managed in orbit. The ISS treats what would normally be considered waste as something valuable that can be recovered and used again. The ISS is one of the clearest working examples of a semi-closed environmental system used continuously by humans. It does not create every resource perfectly from nothing, but it does recover, recycle, and carefully manage many essentials needed for life. That makes the station an important model for future long-duration missions, where efficiency and reuse will matter even more. Canadarm2 is part of Canada's contribution to the ISS. This robotic system is one of the station's most recognizable and useful external tools. and it represents a major Canadian role in the project. It shows that the international partnership extends beyond modules and laboratories to include advanced robotics as well. Canadarm2 is 17 meters long. That makes it a very large robotic arm, capable of reaching across substantial portions of the station's exterior. Its length allows it to move equipment, handle vehicles, and support operations that would otherwise be much more difficult in orbit. Canadarm2 was extensively involved in assembling the orbiting laboratory. This means it was not merely added after construction was complete, but helped build the station itself. In that sense, the robot is part of the history of the ISS as much as part of its present-day operations. Canadarm2 helps perform station maintenance. Many important tasks outside the station require controlled movement, stable positioning, and precise handling, all of which a robotic arm can assist with. By supporting maintenance, Canadarm2 helps keep the station functioning safely over the long term. Canadarm2 helps move supplies. Hardware and cargo outside the station cannot simply be carried around in ordinary ways, so a large robotic arm becomes extremely valuable. It helps reposition and manage materials in a place where human access is limited and often difficult. Canadarm2 helps move equipment. This includes not just small tools, but large pieces of hardware that may need to be relocated or installed. The ability to move equipment with robotic precision is one of the reasons the ISS can support complex external operations. Canadarm2 can also move Dexter. That means one Canadian robotic system can assist another, creating a flexible robotic partnership outside the station. Together, these tools allow the ISS to perform highly specialized work without requiring astronauts to do every task directly by hand during spacewalks. Canadarm2 can even move astronauts during operations. This gives crews another way to reach work sites outside the station safely and efficiently. Instead of depending only on handrails and manual movement, astronauts can sometimes be transported by the robotic arm to support external tasks. Canadarm2 performs cosmic catches by grappling visiting spacecraft and berthing them to the ISS. This is one of its most famous jobs, because some cargo spacecraft approach the station but are not designed to dock entirely on their own. The robotic arm reaches out, captures them, and helps place them into their connected position. Canada's ISS robotics contribution includes Canadarm2, Dexter, and the Mobile Base System. Together, these systems form a broader robotic infrastructure rather than just one isolated tool. This contribution gave the station a highly capable set of external mechanical helpers for assembly, maintenance, and logistics. NASA Facts page describes Canadarm2 as a 55-foot robotic arm. This is another way to express its impressive size in more familiar units. A robotic arm that long is not a small manipulator, but a major structural tool designed to work across the exterior of a very large orbital complex. NASA also says Canadarm2 has 7 joints. Those joints give it flexibility and allow it to bend and position itself in ways that support complicated tasks. Much like a human arm, but far larger and more specialized, its jointed structure gives it reach combined with control. NASA says Canadarm2 has 2 end effectors, or hands. This means it can attach, grasp, or anchor itself from either end, depending on what the operation requires. That feature makes it especially adaptable and helps it move around the station's exterior in versatile ways. Canadarm2 is used to move entire modules. This shows just how powerful and precise the system is, because station modules are large and extremely important pieces of hardware. Moving a whole module in orbit requires careful control, and Canadarm2 was built to support that kind of high-stakes work. It is also used to deploy science experiments. Research hardware placed outside the station often needs to be installed or positioned accurately, and the robotic arm helps make that possible. In this way, robotics directly support the station's scientific mission, as well as its construction and maintenance. It can also transport spacewalking astronauts. This gives astronauts another mobility option during external work and can help them reach locations that would otherwise take more time or effort to access. It turns the arm into not just a construction tool, but also a support system for human activity outside the station. Dexter is another Canadian robot used on the station. Unlike Canadarm2, which is known for its long reach, Dexter is more focused on detailed robotic work. Together, the two systems expand what robotic operations can accomplish on the ISS. The Canadian Space Agency describes Dexter as a versatile robot. That versatility is important because station operations involve many different kinds of tasks, from handling hardware to supporting repairs. A robot that can adapt to varied jobs becomes especially useful in an environment where sending humans outside is time-consuming and risky. Harmony's exterior serves as a work platform for Canadarm2, linking the station's robotics operations directly to its central connecting node. This means Harmony plays a role not only inside the station but also in how robotic tasks are carried out outside. The module therefore supports movement, connection, utilities, and robotics all at once. Cupola houses the robotic workstation from which Canadarm2 is controlled. This arrangement brings human observation and robotic control together in one place. From the cupola, astronauts can look outward while managing robotic operations, which makes the process more intuitive and closely connected to what is happening outside. The ISS integrated truss structure consists of 11 segments plus a separate Z1 component. This truss is like the station's long external backbone, supporting many critical systems across a wide span. Its segmented design reflects how the ISS was assembled piece by piece, with each major section adding new capability. That truss structure provides attachment points for the solar arrays. Since the station depends on large power-generating panels, it needs a strong framework to hold them in place. The truss gives those arrays the support they need to function as part of the station's energy system. It also provides attachment points for thermal control radiators. In orbit, controlling temperature is just as important as producing electricity, because equipment and living spaces can overheat if excess heat is not managed. The truss helps support the radiators that release unwanted heat into space. It also provides attachment points for external payloads. This means the truss is not only structural, but also part of the station's research and operational usefulness. By giving outside instruments places to be mounted, it helps turn the exterior of the ISS into an active scientific platform. The solar arrays were delivered with the S3/S4 truss. That shows how power systems were added as part of major structural assembly steps, rather than all at once. The station's growth involved expanding its ability to generate electricity as new truss elements were brought to orbit and installed. The solar arrays were also delivered with the P3/P4 truss. This means the station's power-producing structure was built up in stages across different sections of the truss. The ISS gradually gained its full electrical capacity through repeated assembly missions, each adding another important piece. Destiny provides interfaces for 24 equipment racks. In a laboratory module, racks are the organized spaces where systems and experiments are installed, powered, and used. Having room for 24 of them means Destiny was designed as a serious working laboratory, with enough structured capacity to support a wide range of station functions. Those Destiny racks support both station systems and scientific research. That means the module is not dedicated only to experiments, but also helps support the practical operation of the station itself. On the ISS, science and infrastructure often live side by side. with the same module helping keep the outpost running while also serving discovery. Radiators were delivered with the S1 truss. These radiators are important because the station must get rid of excess heat produced by electronics, machinery, and daily operations. In space, heat does not simply drift away the way people might imagine. So hardware like this becomes essential to keeping the station within safe operating temperatures. Radiators were also delivered with the S3 truss. That means thermal control was expanded step by step as the station grew larger and more capable. As more systems were added, the need to manage heat also increased, so additional radiator support became part of the station's gradual evolution. Radiators were also delivered with the S6 truss. This reflects the continued build-out of the ISS thermal control network across multiple assembly stages. The station's ability to shed heat had to grow along with its electrical systems, laboratories, and support hardware. Radiators were also delivered with the P1 truss. Again, this shows that thermal control is spread across the wider structure of the ISS, rather than concentrated in one small place. Heat management is a station-wide need, woven into the design of the outpost as a whole. Radiators were also delivered with the P3 truss. Each additional radiator element helped strengthen the station's ability to stay thermally balanced in orbit. This quiet engineering function is one of the reasons the station can support so many systems without overheating. Radiators were also delivered with the P4 truss. Taken together, all these radiator-related truss elements show that controlling temperature in space requires large, dedicated hardware spread across the station's exterior. It is one more reminder that the ISS is a carefully balanced machine, as well as a place where people live. New rollout solar arrays called Erosa are being installed to augment the station's 8 main solar arrays. This means the station's power system is not fixed forever, but can be upgraded as the years go on. Even an orbiting outpost that has been operating for decades can continue to evolve through newer technology. NASA reported that installing 6 1-ROSA increased station power generation to more than 250 kilowatts combined, which represented over a 30% increase. That is a substantial improvement, especially for a laboratory that depends on electricity for nearly everything it does. More power means more flexibility for station systems, science, and long-term operations. NASA later requested 2 additional iROSA to add about 15 kilowatts more power. This shows that upgrading the station is an ongoing process, guided by future needs rather than only current ones. The ISS is therefore not frozen in the moment of its original construction, but continues to be improved as technology and mission demands change. 4 different cargo spacecraft families have delivered science, cargo, and supplies to the ISS: Cygnus, Dragon, HTV, and Progress. This variety shows how station support depends on multiple transportation systems rather than just one vehicle. The ISS has become a shared destination served by several spacecraft types, each helping sustain orbital life and research. Harmony's docking adapter ports were specifically intended to support commercial crew vehicles. That design choice reflects the station's transition into a newer era of human spaceflight, where private sector spacecraft became part of crew transportation. Harmony therefore helps bridge earlier government-led station assembly with later commercial access to orbit. International docking adapters were planned for the station's 2 open pressurized mating adapters. These adapters help create standard connection points for newer spacecraft, making docking more flexible and compatible. In practical terms, they help the ISS welcome modern visiting vehicles in a more consistent and reliable way. Those pressurized mating adapters are connected to the Harmony module. This places them right at one of the station's major connecting hubs, where visiting spacecraft can join the complex in a central and useful location. It also shows how Harmony became important not only for laboratories, but also for transportation architecture. When an international docking adapter arrived, the robotic arm was used to remove it from Dragon's trunk. That is a gentle example of how robotic systems and spacecraft deliveries work together on the ISS. Hardware does not simply appear in place on its own. It must be carefully extracted, positioned, and prepared for installation. Astronauts then attached the adapters during spacewalks. This means the final installation combined robotics with direct human work outside the station. Many ISS assembly and upgrade tasks happen through this partnership between careful machine handling and skilled astronaut effort in the vacuum of space. Each international docking adapter was built by Boeing with parts from companies in 25 US states. That gives a sense of how broad the industrial effort behind even one station component can be. A piece of hardware that seems small in orbit may represent a large network of manufacturing and engineering spread across many places on Earth. RSC Energia made the primary structures of the international docking adapters. This is another example of the international nature of station hardware, where one organization may produce a major structural element that becomes part of a wider shared system. The ISS often brings together contributions from many sources into one final working design. Each international docking adapter measures about 42 inches tall. That gives a clearer physical sense of the device, showing that it is compact compared with full station modules, but still large enough to serve as important connection hardware. In space engineering, even relatively small interfaces can have major operational significance. Each adapter is about 63 inches wide. This width helps accommodate the geometry needed for visiting spacecraft to align and connect safely. Docking hardware has to be precisely designed because it becomes the mechanical and pressure-sealed meeting point between separate vehicles in orbit. With docking targets and related hardware around the outside, each international docking adapter has an outer diameter of about 94 inches. That larger total size reflects all the extra elements required to help spacecraft approach, align, and connect correctly. What might look like a simple ring is actually a carefully designed guidance and interface system. The most recent station module listed by NASA is the Pritchell docking module, added on November 26, 2021. This fact shows that even after many years in orbit, the station has continued to receive new structural additions. The ISS has had a long life, not only through maintenance, but through ongoing physical growth as well. Commercial modules on the ISS include Beam. This is significant because it shows that the station includes not only government-built hardware, but also privately developed elements. The ISS has gradually become a place where public and commercial space efforts meet in a shared orbital environment. Commercial modules on the ISS also include the NanoRex Bishop airlock. This adds another example of commercial participation in station operations. Over time, the ISS has become not just a laboratory for science, but also a platform for new kinds of orbital services and partnerships. Beam is an expandable habitat technology demonstration. In other words, it was designed to test the idea that a habitat can launch in a more compact form and then enlarge after reaching space. This concept is especially interesting for future exploration, where saving launch volume can make a major difference. Expandable habitats reduce the amount of launch volume needed on a rocket. That is valuable because rocket space is limited and expensive, so anything that can fit compactly for launch has a practical advantage. A habitat that expands later offers a smart way to balance launch limits with the need for roomy living or working space. After deployment, expandable habitats can enlarge into a more usable interior volume. This means they can begin as something tightly packed and later become more spacious once in orbit. It is a simple but powerful idea. Launch small, then live larger. NASA says such habitats can provide a degree of protection from solar radiation. This matters because radiation is one of the constant environmental hazards in space. If expandable structures can help reduce that exposure, they may become very useful for longer missions farther from Earth. NASA also says they can help protect against cosmic radiation. Cosmic radiation comes from beyond Earth and is one of the major challenges for human spaceflight. Any habitat design that offers even partial protection from it becomes especially important when thinking about the future of orbital and deep space living. NASA also says they can help protect against space debris. Even small pieces of debris can be dangerous in orbit because of their high speeds. So the possibility that expandable habitats may help shield against this risk adds another layer to their value. NASA also says they can help protect against atomic oxygen. In low Earth orbit, atomic oxygen can slowly erode exposed materials over time. Protection from this effect matters because station and spacecraft hardware must remain durable in the harsh orbital environment. NASA also says they can help protect against ultraviolet radiation. Ultraviolet exposure in space can degrade materials and affect long-term performance. So, if an expandable habitat can reduce that exposure, it becomes more promising as a durable space structure. Beam launched on April 8, 2016. That date marks the beginning of this particular technology test in orbit. It shows how the ISS continues to serve as a proving ground where new ideas about living and working in space can be tested in real conditions. Beam was installed on April 16, 2016. Installation turned it from cargo into a connected part of the orbital complex. This step is important because launch alone is only the beginning. A space habitat concept becomes meaningful when it is actually integrated into station operations. Beam was expanded on May 28, 2016. That was the moment when the habitat demonstrated its core idea by increasing in size after reaching orbit. The expansion showed that the concept of compact launch, followed by enlarged usable volume, could work in practice. Its hatch was opened on June 6, 2016. Opening the hatch meant the module could begin to be used and observed from the inside as part of station life. That turned the technology demonstration into something more immediate and practical within the orbital environment. Its mission was extended on December 4, 2017. This extension suggests that the module remained valuable enough for continued use and observation beyond its original plan. In space operations, an extended mission often means a system proved useful, interesting, or durable enough to justify keeping it active longer. The station supports more than 20 research payloads outside the complex at once. This means the exterior of the ISS is not empty structural skin, but an active scientific environment. Instruments on the outside can observe Earth, study space, or test materials directly in the real conditions of orbit. Those external payloads can include Earth-sensing equipment. From its path around the planet, the station offers a powerful vantage point for observing clouds, land, water, weather, and environmental changes. This makes the ISS useful not only for space science, but also for watching and understanding Earth itself. They can also include materials science payloads. Space is a demanding environment, so it is a valuable place to expose materials to vacuum, radiation, atomic oxygen, and temperature extremes. Studying how materials behave there can help improve spacecraft design and other advanced technologies. They can also include particle physics instruments such as Alpha Magnetic Spectrometer 02. This shows that the station's research role extends into very fundamental questions about the universe. The ISS is not only a home and workshop in orbit, but also a platform for instruments studying cosmic particles. The Alpha Magnetic Spectrometer 02 has collected data on more than 100 billion cosmic particles. That is an enormous amount of information gathered high above Earth, offering scientists a rich dataset for understanding high-energy phenomena in space. It is remarkable that an orbiting laboratory can host an instrument working on questions this deep and this large in scale. Instruments on the outside of the ISS, including NICER and MAXI, have advanced the study of pulsars and black holes. That means the station contributes not only to practical engineering and biology, but also to astrophysics. From low Earth orbit, the ISS becomes a place where the universe itself is studied in new ways. The ISS has become a platform for growing fresh food in microgravity, and astronauts sampled their first space-grown salad on August 10, 2015. This is a wonderfully human kind of research, because it connects orbital science directly to daily life and future exploration. Growing food in space matters for nutrition, self-sufficiency, and the possibility of longer missions beyond Earth. ISS research enabled the first complete sample-to-sequence identification of unknown microbes in space, carried out aboard the station in 2017. That means biological analysis in orbit reached a point where unknown microbes could be identified without needing every sample to be sent back to Earth first. It is a subtle but important step toward more independent scientific capability in space. All of these details together show the station as something more than metal, software, and motion. It is a place where power is gathered from sunlight, where air and water are carefully renewed, where tools reach outward into orbit, and where people continue the quiet work of learning how to live beyond Earth. High above the world, circling in patient loops, it remains a calm human presence in the darkness, moving steadily on.